Lab 6, Magnetic Molasses. The purpose of this lab is that we're going to collect real-world data of a bar magnet falling through a conductive hollow cylinder, also called an aluminum foil roll. Then we're going to use this data found to apply and observe Faraday's law. After that, we create a computational model in Python, and we're comparing this to the results we got from our data collection. So the lab setup. We have a tube of aluminum foil that we're going to drop a bar magnet through. And we're going to collect the time that it takes for the bar magnet to fall through this aluminum foil. So when I play this video really quick,
Yep.
you'll see that the bar magnet doesn't fall in a free fall fashion through the aluminum foil tube. And why is this?
Yep.
This is due to Faraday's law. And so if we start from scratch, we know that magnetic flux is this vector um, pointing perpend. We know that magnetic flux is this vector pointing in the B field direction that is a product of the magnetic field and the area perpendicular to the magnetic field. So in this loop right here, we're basically modeling the entire aluminum foil roll as this infinite set of like conductive rings. And so here, right here, this diagram is just modeling one of those conductive rings. So we have this bar magnet creating this B field going down, so that's why the flux is downward. And then as the bar magnet falls, the B field or this flux vector gets a lot larger. And this is actually going to create a current counterclockwise going in this conductive loop. But why is that? That's because of Faraday's law. It states that the EMF is equal to the negative change in magnetic flux over time. So we know our change in magnetic flux is going downwards because it's increasing in that negative y hat direction. But our negative change in the magnetic flux is actually upwards. And so we use the right-hand rule, pointing our thumb upwards and our fingers curling around to represent the electric field created, also the current around the loop. And we can also use the right-hand rule to figure out what direction is this, I guess, counteractive or resistant B field going to be pointing. Intuition tells us it's up, but if we point our our right thumb to the right and we curl our fingers around, we see that the B field does point up from these eddy currents produced from Faraday's law. And so this creates this resistive force, which is why the magnet does not fall through the aluminum foil tube in a free fall fashion. So here were our drop times, and our average was 1.43 seconds. In the PDF that's on the lab report, you can check out the code, but this is just the results from the code. Our computational model basically suggested that it should fall through in 0.383 seconds, and our actual tested answer was 1.43 seconds. And so these differ by a pretty big margin. And so why is that? We think that this could be due to the collisions with the side of the foil roll. Um, these collisions could basically slow down its descent. Also, the bar magnet is not pointy. Its its faces are flat, so there is air resistance affecting it. And we also suggest that there's a little bit of error and time collection. And so what if the resistivity of the conductor was close to zero? How would the dynamics of this falling magnet change? Well, if the resistivity of the conductor was close to zero, then more current could flow, and thus there would be a higher resistive force to the bar magnet falling down. So it would take a lot longer for this for this bar magnet to fall through the tube. And what if holes or slots were cut into the tube? This would cause the bar magnet to fall way quicker through the tube, since if there's holes or slots, basically this would result in like a broken circuit. Current would not be able to flow in a circular fashion around the tube, creating that resistive B field. Thank you for watching.